Hi, in this segment we shall look at a particular tree-like graph structure that isn't strictly a tree in our definition, but that is very closely related to it: unrooted trees. An unrooted tree is defined as what you get when you take a tree and add the inverse of its link relation to it. Or in other words, an unrooted tree is a graph whose edge relation is the symmetric closure of the link relation of a tree. Note that since the edge relation is symmetric, an unrooted tree is also an undirected graph. And so we can represent it as a tree without directed links. However, because of that, unrooted graphs can be drawn in multiple equivalent ways. And so there is no unique visual representation of them. In fact, you can think of picking up any node of an unrooted tree, and the rest would always drop down and form a tree under it. Since therefore there isn't really a root in an unrooted tree, one often drops the top to bottom layout of traditional trees and represents them as growing in all directions, as in the example in the top right. An important application of unrooted trees is as so-called spanning trees of undirected graphs. A spanning tree is an unrooted tree that is contained within a graph. Suppose you have an undirected graph, that is one where the edge relation is symmetric. The graph has to be connected so that it doesn't contain multiple unconnected subregions. By removing a few edges, we can turn it into an unrooted tree. This tree is a spanning tree of the graph because it spans or connects all its vertices into an unrooted tree by only using edges that were contained in the original graph. This here would be another spanning tree of the same graph. In fact, there are usually many spanning trees for a given graph. They're derived from the original graph by removing edges until the n-node graph contains only n-1 undirected edges, while maintaining connectedness, which means without splitting the graph into several unconnected parts. An example that involves computing a spanning tree is the so-called spanning tree protocol, which is part of network protocols such as Ethernet. In spite of its relative simplicity, it's an interesting algorithm not only because it computes spanning trees, but also because it does so without centralized control. It's a proper distributed algorithm. Suppose you have a network like this, where the clouds represent subnetworks and the numbered boxes are the bridges between them. Bridges have ports that listen to the network traffic in each subnetwork and through which the bridge can forward packets into those subnetworks. But as you can see, the network contains cycles. This represents a problem when forwarding messages, because they can continue to circulate and possibly, when forwarded into multiple directions, multiply, which, especially with multicast and broadcast messages, tends to lead to a situation called a broadcast storm, where the system floods the network with circulating and replicated packets. We would therefore like to configure the system in such a way that links be temporarily disabled so as to make the network acyclic, to eliminate cycles, while, of course, maintaining connectedness. This sounds like a spanning tree needs to be found, and bridges supporting the spanning tree protocol do so whenever they connect or disconnect. This is done roughly as follows. First, one of the bridges needs to be elected root bridge. It is no real root, of course. We're working with undirected graphs and are about to build an unrooted tree, but it is the node that for the duration of the protocol plays a special role. It can, for example, be identified as the one with the smallest ID in the network, as in this example. After the root bridge has been agreed upon, every bridge identifies one of its ports as root port. This is typically the one from which the root can be reached with least delay, for example, or some similar metric. Then the bridges connected to each segment need to agree which of them will forward the packets leaving the segment. Again, based on some metric concerning the quality of the connection of that segment to the root. This time, though, in comparison with the other bridges connected to the same segment. The result of that negotiation is the identification of one so-called designated port for each segment through which the external traffic will leave and enter that subnetwork. Finally, all bridges block all ports that are neither root ports nor designated ports, in effect logically removing all edges that are not part of the spanning tree and thus making the network acyclic. This algorithm is rerun whenever a link fails or new links are being connected. And this is the spanning tree that this run of the spanning tree protocol would construct.